Here's the pH scale. You'll notice it goes from 0 to 14, but actually it goes less than 0 and more than 14, and we'll see that in this video. So a pH of 7, that's what we say is neutral. That would be something like pure water at 25 degrees Celsius, right? At 25 degrees Celsius, pure water has a pH of 7. Other things you may have heard of, milk. Milk would be about 6 on the pH scale. Actually, let's label that. Milk. Normal rainwater is actually slightly acidic. That's about a pH 5.6. So let's go about here. So rainwater is actually slightly acidic. That's because it's dissolved some CO2 up in the atmosphere, and that's made carbonic acid. So slightly acidic. Black coffee would be about a 5. Tomato juice about a 4. Apple juice about a 3. Let's put that one in there. That's a good one to know. Apple juice. Yep, that's acidic. Oh, wait, can't fit my juice. There we go. What else we got? Lemon juice is even more acidic. That's about a 2. So here we go, 2. Oh, wait, what's the circle doing there? That's not a 2. That's a 2. So 2 for lemon juice, even more acidic than apple juice. The pH of the acid in your stomach, so that's hydrochloric acid, and that's gastric juice to do with the stomach, but that's about a pH 1. All right, now up the other end, you'll notice we've gone less than 7 is acidic, right? It says right here, less than 7, you're an acid. More than 7, you're a base or an alkaline solution. So eggs are about an 8 on the pH scale. Hand soap tends to be about a 10. Bases are used in cleaning products, so you want to get yourself clean. It's likely to be a base. Ammonia solutions, probably 11. Bleach would be about a 12. So these are just some common things that you'll come across that are either acidic or basic, right? Now, pH scale. What the heck is the pH scale? Let's have a look. pH. Think of it as the power of hydrogen. Actually, it's the hydrogen ion, and technically it's not even that. It's the hydronium ion, but we'll get to that in a second. In fact, you know what? We'll get to that right now so that we can finish this equation. We'll come back to this equation. What is an acid? Well, there are a couple of definitions of an acid. One is that an acid will release hydrogen ions in a watery solution, right? So in an aqueous solution. Another is that it's a proton donor, right? So hydrogen ions or proton donor. Well, these are essentially the same thing, though, aren't they? Because a hydrogen ion is just a proton. Okay, so actually, well, two definitions. Release hydrogen ions or be a proton donor. Well, hydrogen is a proton in the nucleus and an electron going around the outside. Now, if it's an ion, it's lost that electron. So what is left? A proton. There we go. These things are essentially the same thing, right? So being able to release a hydrogen ion or being a proton donor, these are two different definitions. One's the Arrhenius definition, one's the Brunstad-Lowry definition, but they are essentially the same thing. Now, so if we go with a proton donor for an acid, that means the other end of the scale, the base, we have a proton acceptor. So if we just write that down, a base is a proton acceptor. And we'll talk about bases a little bit towards the end of this video. It's quite straightforward to work out the pH of an acid, or I should say a strong acid. We'll mention that in passing. It's one extra step to work out the pH of a strong base, and for a weak acid or base, it's doable, but not in this video. We'll save that for a later date. But yeah, there we go. So that's what an acid is. It's a proton donor. It releases hydrogen ions. Here's the thing, though: the hydrogen ion, which we said, remember, is just a proton. Okay, that is teeny, tiny. It's really small. And yet it has an entire positive charge all to itself. That means that it has a very intense electric field. Now, part of the definition of an acid, right, is proton donor, lovely. The other half in a watery solution, so in an aqueous solution. So we've got H2O molecules, right? That's what's actually in the beaker there, not just the acid particles, lots and lots of water molecules. Now, because that proton has an intense electric field, it is not going to stick around by itself, no siree. It is going to hook up with the nearest water molecule that it comes across, and there are lots of them in that beaker of water, and it's going to form this H3O plus. Now this has the funky name of the hydronium ion. So we talk about acids being proton donors or releasing hydrogen ions, but what you need to be aware of is that you will never, ever, ever actually have any aqueous hydrogen ions. You will only ever have the hydronium, because as soon as you get a hydrogen ion, it hooks up with the water molecule to form the hydronium. So when we're talking about pH, which we are, pH equals, we've got a simple little mathematical equation for this. The pH is equal to the negative log to the base 10. Now you don't need to worry about your to the base 10, your calculator will just do that anyway, but it's of the hydrogen ion concentration. Now, when we're talking concentration, we actually use square brackets. So let's introduce that concept. Square bracket says concentration. There we go. So that's pH. But really, and this is essentially saying the same thing, but that is really the negative log to the base 10 of the, remember that word, hydronium ion concentration, H3O plus. So that's our formula that we have to work out the pH. So it's quite a straightforward equation. We just take the log of the hydronium ion concentration, and whatever that equals, we'll take the negative of that answer. So let's use our equation and actually determine the pH of some acids and bases. Now, we're starting with nitric acid, 0.5 molar. We need to talk about this thing here, molar. What is that? Well, let's go back to a blank screen. We're looking at 0.5 m. M, capital M, says molar. And molar is a different way to say mole per liter. Okay, I write it like this, mole per liter. You could write it like this, mole per liter. Entirely up to you. I prefer my units on one line. Anything raised to a negative indice means that thing is on the bottom line, right? So that capital L, the liters, is actually on the bottom line, so it's mole over liter. Mole per liter, grand. So mole per liter or molar, these are both a way to say the concentration, because mole, right? A mole is the SI unit for amount of a substance, and in this case we're using liters, not the SI unit, but we're using the liters unit for volume. The SI unit for volume is actually meters cubed, but in chemistry we like to use liters. Physicists can take their meters cubed when they do their thing. So we have mole per liter, that's the concentration. Okay, what are we talking about? Well, we're talking about the acidic hydrogens. Now, if we write the formula for nitric acid, the formula is HNO3. Right? This is nitric acid. Actually, that's not. That's hydrogen nitrate. If we want to call it nitric acid, we make it aqueous. Remember, part of the definition is it will release hydrogen ions. It'll be a proton donor. Yes, in a watery solution, so in an aqueous solution. So all acids that you ever play around with will be in aqueous solution. Right, so now this actually only has one hydrogen that can bug out as a hydrogen ion, which will become the hydronium ion, right? It has one, what we call acidic hydrogen. So if this is the concentration, this 0.5 mole per liter, in fact, we can't see the zero. Oh, there it is. There we go. That's better. So if there's our concentration of the nitric acid, that will also be the concentration of the protons, of the hydrogen ions that are released. It's a 1 for 1. For every 1 HNO3, we get 1 H+. Okay, so that is our hydrogen ion concentration. So now we just plug that in and we say pH equals the negative log to the base 10 of the hydrogen ion concentration, which equals, and then we just do the calculation on that. Now, let me just reach for my calculator. Well, it's my phone, but anyway, it does the job. Let's see, the negative log of, what are we saying, 0.5 equals 0.3, and I'm just going to round this to 1 dB. P, 1 decimal place. Remember, when you're rounding, you should always show your rounding. So that's the pH of nitric acid, half molar nitric acid. So there we go, it has a pH of 0.3. See, that's really not too bad, is it? We can find out the pH of things. Right, let's find the pH of this. This is 1 molar or 1 mole per litre hydrochloric acid. So we could start with the formula, if you like. It's aqueous. If it's not aqueous, we're just talking about hydrogen chloride, and that's actually a gas. So we have 1 mole per litre of this. Well, for every one of these, we are going to get 1 of these, right? Again, we have a 1-to-1 mole ratio, just like we did with nitric acid. So this is a monoprotic acid, right? It will dissociate, it will break apart. That's what acids do, they dissociate to release their hydrogen ions. So it will dissociate to release 1 hydrogen ion. It is a monoprotic, 1 proton gets donated. So let's just go straight to our equation. pH equals the minus log to the base 10 of, in this case, 1, which equals, let's see, minus... Oh, hang on, clear my previous one. Okay, minus log of 1 is equal to 0. Well, okay, there we go. pH of 0. That's right at the bottom of the pH scale, isn't it? Well, no, it's not. As we mentioned, we will actually get less than 0. Okay, the pH scale often is shown 0 to 14, but you can go less and you can go more. Now, let's have a look here. We're going to get less than 0 in this case. This is sulfuric acid. Now, sulfuric acid, the formula is H2SO4. So this actually has 2 hydrogen ions that can be released. For every 1 H2SO4, we are going to get 2 H+. Okay, this is a diprotic acid. Okay, the first two, nitric acid and hydrochloric acid, are monoprotic acids. This is a diprotic acid. So, if the concentration of the acid is 2 molar, but we're getting twice as many hydrogen ions, that means that the concentration of the hydrogen ions is going to be 4 molar. Okay, twice as many hydrogen ions as we had acid particles. So we do need to factor that in before we actually do the pH calculation. So now we have pH is the minus log, and of course you wouldn't need to write everything out each time, but I will. So minus log of the hydrogen ion concentration, which is the minus log, let me put this in, minus log of 4 equals. And we have a pH of negative 0.6, again, to 1 decimal place. Okay, so just need to be careful with this sulfuric acid because it is a diprotic acid. Whatever the concentration of the acid is, we actually have to double that because we're getting twice as many hydrogen ions released. Back to hydrochloric acid, so this is monoprotic, so our pH is equal to the minus log of the hydronium ion concentration, or the hydrogen ion, and in this case it's going to be the same as the concentration of the acid. Reach for my calculator, minus log of 5 equals negative 0.7. It's minus 0.6989. Let's just round it to 1 decimal place and call it minus 0.7. So when you get a feel for working out the pH, it's actually quite a quick exercise, right? Now, here's a different way to show a concentration. Okay, 70%. Wait. Well, when you know a little bit more about acids, and we won't go into this right now, but this is quite concentrated nitric acid, but it has a molarity, a concentration, that's right, concentration of the H+, of 15.8 molar. Okay, you're just going to have to take my word for this one. Like I say, when you deal with acids more, you'll be able to work that out, no problem at all. But there we go, there's our concentration. It's a monoprotic acid, and that's the concentration of hydrogen ions. So pH equals I'm not even going to write it all down this time, it's the minus log of 15.8, which equals minus 1.2. Okay, so we can definitely go less than 0, all right, because this is pretty concentrated nitric acid. It's not stuff that you find lying around all over the place. But, in a high school, we have it, so it's all good. and it's got a minus 1.2 pH. But guess what? We can go lower than that, because here's some good stuff. Here's sulfuric acid. Now, this is 95 to 98% sulfuric acid. It's very concentrated. Now, 95 to 98%. Well, if it were 95%, that would have a hydrogen ion concentration of, 17.8 molar. If it were 98, wait, 98 or 89? Let's write that around the right way. If it were 98%, this ditto, that would be equal to 18.4 molar. Okay, for the hydrogen ion concentration. So we've sort of got a combination of these. It's 95 to 98. It's somewhere in that range. Let's call it 18 molar. Okay, so this is 18 molar sulfuric acid. Now, remember, this is a diprotic acid, so the concentration of the hydrogen ions, or the hydronium ions, is actually twice that. So that's actually 36 molar. Right? It's a diprotic acid. So now when we work out the pH, we need to remember it's the minus log of 36, not the 18, right? That's the concentration of the acid, but the concentration of the hydrogen ions that get released are twice as much, because it's diprotic. So we have minus log of 36, and this will be quite negative. What have we got? Minus 1.6, 1.56. Let's go 2 decimals. Minus 1.56. Okay, so definitely, again, below 0. So yeah, you can go pH below the 0. In fact, I think the most acidic thing that we've ever come across was the waste. We call it tailings from mining, so mine tailings, and that was about minus 3.6 pH. So there we go. We can definitely get less than 0. And in much the same way, we can get more than 14 when we go to the base side of things, the alkaline solutions. The thing about that is, how do we do it? Well, pH has a cousin, and its cousin is pOH. There we go. And pH plus pOH equals 14. Okay, this is because the hydrogen ion concentration multiplied by the hydroxide ion concentration is equal to 10 to the minus 14. So that gives a 14 when we add the pH and the pOH. The pOH is done just the same way as the pH. It's the negative log to the base 10 of the hydroxide ion concentration. Okay, because remember when we talked about, well, what is an acid? Where did we talk about that? Here we go, up here. Wait. No, that's not the one. That's hydronium. Here we go. An acid is a proton donor. A base is a proton acceptor. Well, another way to think of a base is that it will form hydroxide ions in a watery solution, right? So acids form hydrogen ions, aqueous solution, and bases form hydroxide ions in an aqueous solution. So we're actually going to be working with the hydroxide ion concentration for a base, and then calculating the pOH, and if we take that away from 14, that will leave us with the pH, right? We'll just rearrange this equation. We'll take this plus pOH, dump it over here. It's now minus pOH. It's not on this side anymore, and ta-da! That leaves us with the pH, right? 14, take away the pOH. So let's just do a quick example of that. Here we have sodium hydroxide. Now, this concentration of 0.1, right, that's the concentration of the sodium hydroxide, but we can see the equation. For every 1 sodium hydroxide, we're going to get 1 hydroxide ion. So the concentration of the hydroxide ion is going to be the same, right? 0.1 mole per liter. So we work out the pOH first. Now pOH is the minus log to the base 10 of the hydroxide ion concentration, so that's 0.1 equals, and we'll go back to the good old trusty calculator, minus log of 0.1. Actually, I could have done that in my head. I know how maths works. But anyway, there we go, so 1. So the pH, remember we just showed before, the pH is equal to 14. Take away the pOH, which is 14, take away 1, which is 13. So this sodium hydroxide solution has a pH of 13. Okay, so even though we're talking with the pH, we're talking about the power of the hydronium ion concentration, right? We can actually find it even though if we're talking a base, where we think, wait, no, bases don't have hydroniums, they've got hydroxides, but we can still find it, no problem. Sodium hydroxide, again, so the concentration 4 molar will be the same as the concentration of the hydroxide ions. Let's just scribble that down. That equals 4 molar. So the POH equals the minus log to the base 10 of the hydroxide ion concentration, which in this case is 4, which equals, right, let's see, minus log of 4 equals, now that equals minus 0.6. So here we go. Now we have a negative pOH. But remember, the pH is 14 take away. In this case, we're taking away a negative, so we're going to be adding it. And we don't even need a calculator for this one. 14.6. So here we have a pH that is above 14. So we've seen that we can have a pH less than 0, and now we can see that we can have a pH more than 14. So 0 to 14 is not the end of the story. But you know, it's how it's usually presented, right? So 7 is neutral. Think pure water at 25 degrees Celsius. That has a pH of 7. Now, we should actually also just very quickly look at that whole pure water thing. Pure water's pH, remember, was 7, right? It's not an acid, it's not a base, it's right in the middle, right? Less than 7, you're an acid. More than 7, you're a base. So let's talk about pure water at 25 degrees Celsius, right? Here's some pure water, just H2O molecules. I have nothing else in my beaker. The thing is, some of those water molecules, all by themselves, will break up. Okay, we say water self-ionizes or self-dissociates. Dissociates meaning it breaking apart, or ionizes meaning we're getting ions from it, right? So now we have a hydrogen ion and a hydroxide, a plus and a minus. They will hook up and give us our water molecule back again. So, you know, they don't split up for long into the ions, that we get the water back. But at any given moment in time, we have 10 to the minus 7 water molecules have self-ionized. Right? Which means that that's our concentration of hydronium, because look, I have one water molecule, I get one hydrogen. Remember, hydrogen ion, hydronium ion, you can use those words interchangeably. Technically it's the hydronium, but people often talk about the hydrogen ions. So 1 for 1, which means if I had 2 water molecules, I'm getting 2 hydrogens. If I had 37 waters, I'm getting 37 hydrogen ions. If I have 10 to the minus 7 waters, I'm getting 10 to the minus 7 hydrogen ions. So that is the concentration of the hydrogen ion at any given moment in time. And there we go. If we take the minus log of 10 to the minus 7, we get, oh look, surprisingly, well not surprisingly because we know the pH, we get 7. Okay, so that's why the pH of pure water is 7. Now I say at 25 degrees Celsius because temperature affects this thing. Temperature will affect how many of those hydroxides and hydrogen ions we get. If we change the temperature, we might have to make this arrow smaller because we've got more of the ions. Or if we change the temperature the other way, we might have to make the top one smaller and we get mostly the water molecules and less of the ions. But at 25 degrees Celsius, there we go, 10 to the minus 7, 1 in every 10 million water molecules dissociates or ionizes, so we get 10 to the minus 7 hydrogen ions. That's our concentration, negative log of that pH of pure water, 7. And I guess we'll wrap up the video now. It went a bit longer than I thought, so let's call it done.
Don't forget to hit the like button. Yeah. And subscribe to It's Up Here. And here's another video.